Okay, thanks, Rosanna, for introducing me. I'm going to explain the GSPSpec module, which is a module devoted to the analysis of the RBS spectra derived from the CU6. This is the scheme of my talk today. I will start with an overview of the RBS spectra, because not everybody may have been in the previous talk, the previous webinar. And then we'll continue with the explanation of the characteristics of the GSPSpec module and its output. As you may know, Gaia is a revolution. Gaia is the most advanced astrometric mission to date. Since its launch in 2013, it continues the legacy of Hipparcos by providing precise positions, parallaxes, and proper motions for more than 1 billion sources with errors of few microns, with an unprecedented detail. For a small subset of bright stars, it also provides the radar velocities thanks to the onboard spectrograph RBS. Since the latest Gaia data release, it provides also the chemical abundances and stellar parameters for 5.6 million sources analyzed, whose spectra was analyzed by the GSPSpec module. This is an artistic image of the Gaia focal plane. When I start, can you see my mouse? I guess so.
No.
Okay.
You can, but it's very small. Yes,
yeah.
at least I can. Yeah.
Okay.
Now I see it.
Okay. When a star is detected by the sky mapper, it sends an information to a astrometric unit to track the passage of the star in the along scan direction, just because the perpendicular direction is degenerate for the estimation of the astrometry. Then it's observed by the CCD of the photometer, and finally by the RBS spectrograph. This spectrograph has a resolution power of 11,500 and operates in the wavelength range of the calcium triplet, located in the near infrared, with 846 and 870 nanometers. In the GSPSpec module, we analyze this spectra. One of the main characteristics of Gaia is that it's not a ground-based telescope, but a space mission. So it has many advantages, like the continuous observation. It is a non-stop survey. For DR3, it has been observing for 33 months. And the space offers more stable conditions than the atmosphere. We don't have to deal with the telluric lines or with the weather during the observing time. This allows us to perform a very homogeneous treatment of all the sources. And since it is a continuous observing mode, we have a high number of stars, high number of statistics. We have analyzed millions of sources, and some of them with a very high signal-to-noise ratio. This allows us to get a parameterization quality comparable to those of the ground-based surveys of even higher spectral resolution or larger wavelength coverage. In this image of the week, you can see the chemical elements analyzed by the GSPSpec module. Each line has its own individual window determined individually for each of them. We also detect and measure the diffuse interstellar band. This is a feature in the spectra associated with the extinction. And also we provide the equivalent width, the differential equivalent width of the CN lines. As you can see, there is a total of 12 elements, but we have two types of iron. We measure the neutral iron and the ionized iron, the first ionization of the iron, for very hot stars. Now, small, very quick motivation, scientific motivation for measuring the chemical abundances. The chemical abundances are important because they shed light on the galaxy formation and evolution through the composition of the stars. The chemical elements are synthesized in the interior of the stars and polluted in the stellar medium through different channels. The relative contribution of these channels defines the chemical pattern of a galaxy. For example, it's well known that the thick and the thin disks have different chemical composition, showing high alpha elements and more metal rich and low alpha elements in the thin disk. Now I will describe the GSPSpec module, the workflows that I made in this module, and the characteristics and the grids and the tools we used to estimate the chemical abundances and the stellar parameters. As Rosanna said before, the GSPSpec module is implemented in the Gaia CU8 pipeline. It is the only unique module that analyzes the RBS spectra directly from the CU6 unit. That means we receive the spectra corrected in Doppler shift, and we don't use any information from the astrometry, from the photometry, or for the resolution spectra. There are other modules like Flame or SP that uses our output. So GSPSpec has mainly two workflows. One is Matisse-Gauguin, devoted to the estimation of the stellar parameters and the chemical abundances mainly, and also the ANN. This is a neural network that estimates only parameters. Matisse-Gauguin includes different submodules, different workflows, while ANN is a neural network with 3 layers. The first layer, the first input layer, has 800 neurons, 1 per pixel. We use a rewind spectra from the CU6 of the 100 pixels. Then the output has 4 neurons, while the intermediate layers has different number of neurons from 50 to 100, depending on the signal to noise ratio. These are the products of each module, each workflow. Matisse-Gauguin estimates the stellar parameters, say the effective temperature, the surface gravity, metallicity, and the alpha over iron abundances. Also the chemical abundances for individual elements, 13 individual elements. We also estimate the DIP, the diffuse interstellar band, and the differential cyanogen equivalent width. In the output, we include also some metadata and the flux, which are very important, and one part of my talk will be specifically devoted to the usage of this flux. ANN, on the contrary, only provides stellar parameters and also some flux. This is a description of the workflow of the Matisse-Gauguin for the parameters. This is quite complicated, but I will give a brief introduction of it. First, we take the RBS spectra from the CU6, and a module called DCAS, which is a decision tree, give a first estimation of the atmospheric parameters. It's a kind of a seed. Then this seed is used by Matisse to iteratively update the parameters, performing a multilinear regression method until the convergence. If needed, this process is repeated until the continuum is well subtracted. Basically, it compares the interpolated spectrum with the observed one after performing some sigma clipping procedures. This is very important for cooler stars because we have problems with the continuum. And the goodness of it, the quality of this fit of the continuum is also safe as an output. Once we have an estimation of the atmospheric parameters, we provide them to the Gauguin module, which basically performs a steepest descent method. This is a Gauss-Newton algorithm that explores the grid to find to refine the solution of Matisse-Gauguin. For the abundances, this is only Gauguin is performed after receiving the parameters from the Matisse module. And after that, the spectra is analyzed by the deep module, which basically performs a Gaussian profile fitting for estimating the deep parameters. And after that, also the CN, which is very similar to the deep. Yeah, this is a scheme of the Gauss-Newton algorithm used by the Gauguin module, but it's simply a steepest descent method. For the atmospheric parameters, it used after Matisse, while for the individual abundances, the parameters are not computed, but just assume the ones that provided in the previous step by a combination of Matisse-Gauguin. For the error propagation, we perform 50 realizations of the input spectra, considering the error, and we loop again 50 times. We save the median values and the 84 and 16th percentiles, just consider an upper and lower sigma, and also some metadata in the number of lines that have been used for the abundances. For the mean value, we perform a weighted average in which the weight is the inverse of the uncertainties. The eigenvalue module is a little bit simpler. First, there is a selection procedure in which the spectra is classified depending on the signal to noise. Then we check if there is some artifacts or some problems, zero flux pixels in the input spectra. If so, they are masked. Then perform a min-max normalization and the parameter estimation. The output parameters are not normalized, but there is a procedure of denormalization after it. And like in the case of Matisse-Gauguin, this process is repeated 50 times just to estimate the uncertainties. Here we can see a projection of the synthetic grid we used for the estimation of the parameters. This considers Mark's atmospheric models implemented by turbo spectrum. And the step size is 250 in effective temperature, 0.5 dex in log G. In metallicity, 0.25 dex, while in alpha, because the scale of alpha is lower than that of metallicity, we consider a step of 0.1 dex. This is similar for the individual chemical abundances. Each line has its own grid, extended, of course, with the individual abundances. And for some elements, we also extend in metallicity, including a very metal poor regime from -3 to -5 for the iron, calcium, and silicon, because we observe that we can still provide some abundances in this very metal poor regime for these elements. This is an illustration in a kind of kit diagram in which we overplot the synthetic spectra of alpha-rich star. This is just for the illustrative purposes. You can see the change with the temperature and with log G of the synthetic grid. For the atomic lines, we consider our own list of lines. This list has been refined many times. We started by analyzing high-resolution spectra of the Sun, Procyon, Mu Leo, and Arcturus. And in work done by Gabriele Contursi in 2021, he basically evaluates each line and provides the information needed to classify a line as a good or bad for the Gaia purposes. After that, we re-examine this line list in a spectra of the same stars, but reduced in resolution, blurred in resolution, to guess if they are possible to observe or they are important to observe in Gaia. After this, then there was another extra refinement of the line list based on the quality, basically on the quality of the output abundances. I want to emphasize that in our procedure, we consider two normalizations. The first one is performed over the whole spectra, and the second one is individual of each line. Each line has its own normalization window, called second normalization window, that has been chosen by hand, and exploring myriads of combinations. We tested hundreds of possible combinations for this second normalization window for each individual line, and we conclude that it's better to use wide windows for these normalization lines, for these atomic lines. Also, each atomic line has its own individual abundance determination window, also evaluated after many tests, iterative tests, checking the biases induced by the very large and very small windows. And based on an individual analysis of each line, we decide the optimal choice in a very manual way. For the calcium triplet, this treatment is special because the grids have not implemented the non-LTE effects that are important in the core of the calcium triplet lines. So we measure the abundances of calcium-2 by looking at the wings, at both sides of the wing. You may have seen that some of the lines here has an asterisk. This denotes that they are not individual lines, but many lines of the same element, maybe doublets or triplets, or simply lines of the same element that are very close to each other. Of course, we have tested these lines separately and combined, and we decided to keep them combined because the results were better. So GSPSpec has been running in the DPC Center in Toulouse. It analyzed almost 7 million sources, 50 times each. Remember the error propagation, the random realization of the input data, requiring more than 100,000 hours computing hours spread on the 2,100 cores. This results in a total execution time of 150 hours, basically 1 second per spectrum realization. Now I will explain the output of the GSPSpec. Since you may not be familiarized with the Gaia archive, I will give a brief introduction of it. You can access the Gaia archive by typing this web direction in your browser. It is possible to get access by Python or Tomcat, but it's more advanced, and I think it's not the scope of this talk. Here you can see the ADQL console in which you type the commands to select your stars. ADQL language is basically SQL, so if you have any doubt, you can check in Google both languages, and 90% of the time, commands of SQL are valid for ADQL. Here you can see the list of the data releases and the tables. For our purposes, GSPSpec tables are located here, astrophysical parameters and astrophysical parameters supplementary, which is devoted to the output of the ANN module. And you can upload or download the queries as you wish, also see the first results or send them to the boost space. And of course, you can select the most suitable for you, the format most suitable for you. Like other tables in Gaia, they have been ingested in the Gaia archive. These tables contain approximately 5.6 million sources, and the output of Matisco again is located in the table astrophysical parameters, while the output of ANN is in astrophysical parameters supplementary. You can identify the output of these modules by the name. They contain the GSPSpec suffix in the column name. This is a trick I use to select stars that have been analyzed by the GSPSpec module, in this case the Matisco again. Since there is no specific flag for the stars that have been analyzed by GSPSpec, what I do is select those stars that has at least a measurement of the effective temperature. That means that the effective temperature is not a none, it's not a null value. This results in the 5.6 million sources I mentioned before, and it's quite quick in implementing in just a few minutes. Here I illustrate the power of the GSPSpec module. We can see the map of the sky map of the galaxy color-coded with a medium metallicity. As you can see by a first glance, we can identify many structures in the galaxy. We observe the metal-rich component of the thin disk. In the outer part, the thin disk is more metal poor, so the blue color dominates. We can identify bulge regions of characterized by metal poor values. And these high metallicity points you observe at very high latitudes are not halo stars, but close stars, stars that are close to the solar neighborhood, so they are metal rich. They tend to be metal rich. Also, in alpha, color-coded with the alpha over iron, we see the correspondence between the low alpha regime and the metal-rich values. This structure here is not physical, but is an effect of the scanning law of Gaia. During the observing time, this zone was overexposed, so the signal-to-noise ratio is better here. This allows us to detect fainter sources, and this bias the alpha over iron. This is the output compared to the other big surveys like Apogee, Gala, and Gaia ISO survey. As you can see, we have more sources than the combination of all of them in all the G magnitude range, well, except in the very faint regime. This is the output of the individual parameter number of the individual parameters for each module. The dark green color refers to the raw value, let's say without any flagging, any filtering, while the green ones correspond to the reliable ones after applying some flagging criteria. As you can see, we have measurements of the parameters for millions of sources. The same plot, but for the individual chemical abundances. The light blue corresponds to all the measurements, basically, or the output, and the dark blue refers to those that we have very high quality. For some elements, like the zirconium and neodymium, we cannot provide a huge number of measurements, of reliable measurements, but at least for cerium, we can provide a few hundreds of, almost 1,000 of reliable values. You can see most of the times we provide at least dozens of thousands of individual abundances. It's inevitable to compare our parameters with those of the literature. For the effective temperature, we compare them with those in Apogee, Gala, and Rave, and we observe almost no bias, negligible bias, almost zero, for the region of temperatures. The standard deviation is a little bit larger, but not problematic, and also the median and the median absolute deviation. So we conclude that we have no bias in our parameters when compared to the literature, at least in temperature. But in log G, we observe this same trend, let's say, but shifted. We have a bias that we will have to correct. I will explain how we correct it. And this bias is 0.3 almost. Is a huge bias in log scale, in the scale of the supersonic gravity. And we propose a polynomial correction for it. If we compare the metallicities, we see that there is no an average bias. But if we separate the stars by giants and dwarfs, we observe some biases. The average metallicity of the giants are subestimated, while the dwarfs are underestimated. So we also provide corrections for it. This is the proposed correction. This is a calibration, polynomial calibration based on the uncalibrated log G. Basically, we substitute the uncalibrated value by a calibrated value by adding a polynomial relation. The coefficients of this polynomial relation are summarized in table 3 in Mauricio Blanco et al. But you can see the coefficients here. While during the analysis process, we observed that the stars in open clusters admit a better calibration, so we included it. You can see here in this plot the comparison of the open cluster stars between GSPSpec and the literature, and you can see that with the black curve, which is the specific calibration for open clusters, we slightly improve the calibration, the generic calibration we propose for all the stars. I want to recall that the calibration of the log G metallicity is mandatory, is almost mandatory. When comparing the alpha abundances with literature, we find that our alpha abundances is basically the calcium measurement, because our spectra is dominated by the calcium lines. We find an offset, a shift with respect to the literature, especially with apogee. But if we apply a polynomial calibration, we reduce this bias to almost negligible values, and also the standard deviation is decreased. Here you can see the calibration we propose for the alpha elements and the individual chemical abundances. In general, this calibration depends on the uncalibrated value of the surface gravity, and it has an application range. My personal suggestion is that out of this range in log G, you simply use the extreme values. You saturate the correction. For some elements, we have a very high statistics. We can relax the extra flag condition by admitting values equal or lower to 1. And in this case, we have an alternative calibration with a 4-order polynomial. And it depends on your scientific purpose to use it or to use another one. Also, some alpha elements may need a correction, which depends on the effective temperature. This is the case for alpha and the calcium, which are very similar to each other. But also the sulfur. The sulfur is observed mainly in the hot regime, very close to the border of the grid in temperature. So we observe that some biases can be corrected by using the temperature instead of the surface gravity. This is a statistic test we perform to compare our parameters with those in the literature. In each plot, in each panel, we compare the reference value, the parameter of the GSPSpec minus the literature value over the quadratic sum of the errors. If there were no bias between our parameters and the literature, then we should expect this red curve, which is a Gaussian of unity width of sigma equal to 1, and no bias, centered at 0. But we observe some deviation, and also this deviation is different among the different surveys considered. So our conclusion is that we find a good agreement, but also the discrepancies can be explained by the discrepancies among the literature, because we use different lines, different models, different selection functions. Now, this is the main part of my talk. This is the importance of the GSPSpec flags, because during these months after the DR3, we have seen that people don't use properly our data. They tend to ignore, or simply they don't know that we provide also flags, quality flags for the parameters and for the abundances. There is a total of 41 flags, but we can define 3 different families. One family of flags for the parameters, the stellar parameters, another one for the abundances, and 2 for the deep and the CN respectively. Our convention is that the flag 0 means a good value, while the flag 9 generally means that this value should be discarded. It's not realistic. And the intermediate values ranging from, in increasing order, from 1 to 9. I will explain the V-broad, the first flag you see in the list. This quantifies, defines the bias induced by the effective by the broadening of the line in the effective temperature. Basically, we did many tests with synthetic spectra. We tested different broadening velocities with different rotational velocities. And depending on the degree of the bias induced by this rotational velocity, we classify as a 0, 1, or 2 its flag. Basically, if the rotational velocity is so strong that produces a big bias in effective temperature, we discard it. This is similar for the surface gravity for the metallicity. And the 4th, 5th, and 6th flag is essentially the same, but instead of the rotational velocity, the radial velocity, the spectroscopic velocity we measured with RBS. The rest of the parameter flags are basically defects in the spectra, non-values or emission lines in the spectra. And the last one, the KM flag, is due to some molecular lines that are present in the very cool spectra, and the spectra of very cool stars. This difficults the measurement of the continuum, the subtraction of the continuum, and therefore the normalization. So we obtained a non-physical structure, vertical structure in the very cool regime. So we decided to flag these stars and to set artificially the temperature and the log G to this point you can see here. This is a color and density map of the GSPSpec output. And all the stars that lie in this specific pixel, in this specific position, are stars that have KM flag non-equal to 0. The flags for the abundances, for the individual abundances, are more complex, but I will simply say that they depend on the interval of effective temperature, interval in surface gravity, also the goodness of fitting of the continuum level, and the difference with respect to the extreme values we can measure with our synthetic grid, 5D grid. Also, we account for some border effects and for some relative errors. If they are too big, we flag them as 2 or 9. And for the deep, basically these flags depend on the quality of the Gaussian fitting. We know that the GSPSpec flags are not easy to use by the community because they are distributed as strings by the Gaia archive, but it is possible to perform queries using them. The key is the like keyword. This keyword basically compares two strings, and if they have the same structure, the same shape, it returns true. Otherwise, it returns false. I will illustrate the use of this command with the following example. Let's say if we want to select those stars that have the BRAT-M, the 6 flags in the previous list, equal to 0. So basically, we type this command, flag GSPSpec like, and to substitute any characters, we use the underscore character, and to substitute multiple characters, we use a percentage character. This can be reversed in case it's needed. And this is basically the strategy to select a specific value for the flags. But what if we want a range of value? For example, what if we want to consider the flags that are 0 and 1 or 1? So we have no alternative than the brute force. Basically consider all the possible combinations. If we want to be between 0 and 1, including both, then we have to concatenate these statements with the OR command. My recommendation is that you use parentheses. Remember that the Boolean algebra is not associative in this way, with a normal algebra. So we have to include this parentheses to separate the OR statements for the AND statements. This is the case of the previous query, but adding another condition for the fifth flag. While this query here has no sense. It's the same as the previous one, but without the brackets, and this will give misleading results. So my suggestion is never put the OR and commands at the same level in the query. Alternatively, but not recommended, you may want to download the full catalog or at least the full list of flags and then perform the filtering in Python. So you can download all the flags using this query here. It takes a few minutes and the output is a few megabytes, 700 megabytes. So it's possible for a computer to handle with them. And maybe you want to define a function like the one I proposed to extract the flags from this string of characters. This is basically an optimized loop statement in which the output is the string of characters returned by the Gaia archive, and the output is a list, a vector of integers. Depending on the Python version and the distribution of the output, you may want to tune, you probably will have to tune this code. And also you can use Python just concatenating, you can use Tomcat just concatenating the parsed integer and substring commands, but you have to repeat this procedure for the 41 flags in case you're interested, but it's possible. So there is no excuse in the community for not using our flags. I provide the Python tools, the Gaia archive, and the Tomcat procedure. And now I will.
I'm sorry, Pedro. Just a time check is 10:45.
Okay. I will show some of the results of GSPSpec. Here you can behold the quality of the fitting of a GSPSpec for a hot start as hot as the sun, but lower gravity it is more giant. You can see that the fitting is quite good. We can trace most of the lines. This is one of the amazing results we found with the GSPSpec output. We can measure the ionized iron, and the abundance of this ionized iron correlates very well with one of the neutral iron. As you can see here, the correlation coefficient is very high, 0.8, suggesting that we are in the correct guess of assuming that this is ionized iron. It was a very complicated line because there is not much information about this in the literature. We are able also to detect cerium. You can see that even with a small line and small variation, we can observe it, measure it. Indeed, there is a paper of Gabriele Contursi et al. 2022 in which he explores the cerium abundances of GSPSpec. This is a result concerning the deep. Here we have the color, while here we have the effective temperature, and you can see that the deep informs about the deviation from the theoretical law expected from the Casagrande relation. As the deep increases, the difference with the synthetic with the law is larger. Here I illustrate some key diagrams of the output data. You can see the trend expected in metallicity from the one side to the other of the giant branch, also in alpha. We are able even to identify substructures in the kill diagram. You can see here this bump of stars that correspond to young stars. Of course, we detect the clamp. We identify the giant branch, some stars in the asymptotic giant branch, and a band of stars here. We also observe the dichotomy of the thin disk. You may have seen that these in other elements are more separated, but for the alpha, in our case calcium, they tend to be more close to each other. We cannot separate them, but it's somehow expected. Somehow normal, it also observed in other surveys like apogee. We can observe metal poor stars, but we found an unrealistic number of extreme metal poor stars when we consider those measurements without taking into account the flux. But if we filter properly, we observe a more natural relation in the very metal poor regime. This filtering condition is quite complex, but is summarized in Recio Blanco et al. 2022. This is an example of the fitting of the spectrum of very metal poor stars, metallicity minus 3.5, few lines, but we can detect them. Here, the orange and black line corresponds to the closest grid nodes, upper and lower closest grid nodes to this value of minus 3.52. Now I will show some scientific applications. Yeah, there is a performance verification paper of the Gaia team in which we explore many different applications for the chemical cartography of our data, of the GSPSpec data. I will summarize some of them. Here, for example, we selected 3 different regimes in the kit diagram: the hot ton of stars, the RGB above the red clamp region, and some massive stars. We observe that the hot Talmor sample is quite metal rich because they are very young and they are very close to the sun. For the bright RGB sample, we can observe some azimuthal asymmetries because of the presence of the spiral arms, maybe of the bar. They are more metal poor than the previous one, with an average metallicity of minus 0.4, but we can reach larger distances from the sun. And this sample is concentrated around 3 kiloparsecs from the sun, with spatial homogeneities due to the spiral arms. The internal spiral arms seem to be more metal rich than the inner ones, but they are more metal poor than the prediction of the models. Here we can see that they are more metal poor than expected. Also, Eloisa Pollo was able to detect the spiral arms in the excess of metallicity. She compares the distribution of metals with the distribution of stars in the galaxy, in the plane, with an RGB sample, and she could identify the perceived local and Sagittarius spiral arm in the metallicity excess, defined as the metallicity minus the local metallicity minus the metallicity average over a wider region. In this paper of Spitoni 2023, he found evidences of a third infall by observing metal poor stars, but very young, and also some alpha parameters in common with apogee are in very good agreement, showing similar trends and in general in the same ratio of values. This is the velocity profile of the Milky Way. Here we represent the rotational velocity, azimuthal velocity, as a function of the galactic-centric distance. And we have found some correlations between the excess of metallicity and some ridges identified previously in other works, which are basically connected either with moving groups or maybe a consequence of an incomplete phase mixing of the orbits. Also, we observe some azimuthal variations because in the negative azimuth, one of the moving groups has no counterpart in the positive azimuth regime. This is a work done by Gabriel Concursi about the cerium. He compares the cerium of GSPSpec with those of Apogee and Forsten 2019. And he basically found a good agreement, given the zero bias. When we select properly the quality flags, we perform the calibration, and the discrepancy is larger when the discrepancy with the parameter, with stellar parameters, is also larger. In this plot, we explore the connection between the dynamics and chemistry. I will explain briefly the meaning of this axis. This is the radial action. This is basically a momentum variable that quantifies the epicyclic motion, quantifies the eccentricity, if you want, versus the angular momentum, which is characterizes the guiding radii, the typical distance of the orbit around the galactic center. We observe some overdensities in the density distribution, and this overdensities has a counterpart in the metallicity. We observe different metallicities for different regimes in this diagram. Also for the alpha abundances, we observe that low alpha abundances mean high metal rich values and vice versa. This is an overview of the energy versus angular momentum diagram of the Milky Way. Here, this regime here corresponds to the stars with very circular orbits. This is a solar neighborhood. And as we move towards the low angular momentum regime, we are exploring the halo and the thick disk, and the metallicity tends to be more metal poor, and the technical composition shows an enhancement of alpha elements. We were able also to explore some accreted structures. You can see, for example, in Sequoia that we observe a depletion in the alpha elements characteristic of the accreted systems. Also in Tamnos, for Gaia Enceladus and Helmstein, we have more contamination because the selection is more not so specific, it's more wide, but we can still see a predominance of low alpha stars. Finally, the recommendations.
Pedro, we really have a couple of minutes.
Yes, this is my last slide.
Thank you.
Calibration is mandatory. Always use calibrated values, and please use the flags. As an initial guess, we suggest to set the first 13 flags equal to 0, and then depending on the sample on your proposed, just relax or be more strict with the flags. Also, we have provided many suggestions for the use of the flags in the GSPSpec paper, and also in the PDP you can find many scientific applications of the flags. I will finish with the conclusions to read, and that's all.